Here's the Variomatic Propeller after the ultimate endurance test, 1100 miles unsupported paramotor adventure in the United States. To summarize the conclusions, well, I had some wear on the mechanism. The mechanism failed eventually completely, and it only worked properly in the Death Valley. Everything on an aircraft must have a reason. Ignore the status quo, imagine from scratch, and build what you can justify with science. Fail 5 times to succeed once. This is how we innovate paramotors, and for you, understanding the science behind will make you a smarter pilot. The Wingman Challenge was an amazing adventure. 18 pilots flying unsupported over a long distance, 1100 miles, starting at the Sierras, going down through the Death Valley, around Las Vegas, that was amazing, crossing the Lake Mead, Valley of Fire, Zion, Bryce Canyon, Escalante, Capitol Reef, Factory Butte, crossing the Lake Powell to the Monument Valley, and then flying back up to the Apple Valley. Wonderful, wonderful. Now, I honestly expected that this prop would do magic. I mean, the Variomatic prop is made to save fuel on long cross-country flights, make the long cross-country flights longer, or eventually allow me to take less fuel than others for the same distance. The event was a great success, and the event was a great achievement, and I'm super happy for doing it. But the Variomatic prop definitely didn't perform as expected. 3 results and 3 conclusions. First, I had some wear on the mechanism. Secondly, I lost 1 spring. And thirdly, it didn't work well at high altitude. It only worked great in the Death Valley, but 90% of the flights we did over 6,000 feet, eventually up the way up to 11,000 feet. At that altitude, it didn't work well. So let's go one by one. Let's start with the problem number 1, that's wear. On the first and one and only prototype of the Variomatic Propeller, we have some screws touching some aluminium parts. They act for fine adjustment of the propeller, but obviously this is not a good point. The steel screw basically caused some wear in the aluminium part. Now, I'm not worried about this because I actually expected this to happen. The prototype needed to be smoothly adjustable, but on the final product there will be predefined spacers in the exact length that it's needed, and that wear will not happen again. The second problem was that I lost one of the 2 springs in flight. I've heard something flying through the prop, but I didn't notice anything weird. There was a little bit of high vibration at slightly below level flight RPM, so I continued the flight, and only when I landed I realized the bolt and the spring was missing. This is actually good news because it just proved that the linkage between the propellers worked as intended. So despite the fact that one prop blade lost the spring, you could expect that the 2 blades will behave differently, but they didn't, because there's a linkage between those two blades, so they move simultaneously. So either the linkage worked very well, or even if it didn't, and there was a slight difference between the pitch between the 2 blades, that difference probably doesn't matter that much. So I'm glad this was tested as well. These are all problems easy to solve, or actually I assume they're solved already. Now, the major problem was that it wasn't performing as expected or as it did back home. It wasn't delivering the fuel saving. I know what is the problem, and I only guess what could be the solution. So I may need help of you guys, especially those who are more skilled in engineering and science. So let me describe the problem. On the very first flight, taking off at Bridgeport, 7,600 feet or so, very high elevation takeoff, I burned 8 liters per hour on that particular flight. Horrible. Now, yes, I went through the troubleshooting with tuning my carburetor, so the fuel consumption dropped a little bit, but still the fuel consumption was insanely high. The major problem was that while back home at sea level, with this particular prop, I fly level flight at 4,900 RPM. Over there at that high altitude, we were usually flying over 6,000 RPM, simply because we were mostly flying 6 to 11,000 feet above sea level. So I just guess that as I needed a lot more thrust to maintain level flight at that altitude, I basically added throttle, the prop downshifted to 10 degrees and behaved like a regular 10 degrees pitch prop. So I wasn't using the advantage of the high gear of the 13 degrees in the mid-range, because I was flying in the high range all the time. The only exception that it worked was the Death Valley when we descended at sea level. Basically, it calmed me down because I realized, okay, it's working here, but that was just the one section. The whole Utah, California, Nevada that we were flying over was just above 6,000 feet. The way the prop worked back home, it just didn't work at high altitude. And it wasn't delivering as needed. It wasn't bad, it wasn't worse, it just wasn't better. It wasn't delivering the fuel saving as expected. The Wingman challenge, flying unsupported over unknown terrain in long distances, fully loaded with camping gear and extra fuel, that's not the right environment to do research and development. That's not the right occasion to do fine-tuning of the propeller, yet I tried my best. So what I did, I increased the preload on the spring, hoping that with more force, pushing it into 13 degrees, the downshift will occur a little later. That means even at higher altitude, where I need more RPM and more power, I will still fly in the 13 degree setting and could benefit from lower fuel consumption and lower RPM for level flight. Now, this did happen. When I increased the preload on the springs, I decreased the RPM I needed for level flight slightly. But there was another problem. I wasn't reaching 8,200 or 400 RPM as before. So when I went full power, I only had 7,800. So what had happened, increasing the preload moved the RPM where it downshifts a little higher, but actually as it started downshifting later at higher RPM, it never finished the downshifting. At least this is what I assume. Even at full power, I ended up maybe at 12 degrees or so, it's just a guess. I didn't let the engine to rev up to full power and provide me the full climb. I mean, this was a horrible situation because I really needed the power for the takeoffs. And as said, eventually later I lost the spring, so what I did is I tightened the stoppers to make it a 10 degree fixed pitch prop, so it wasn't moving at all. So I set the low stopper to 10 degrees, I have set the high stopper to 10 degrees and removed the other spring at all. So basically I finished the whole adventure with a fixed pitch prop. And it performed just like any other propeller. Now there is one more interesting behavior of this propeller, and that after I increased the preload, I barely had 8,000 RPM at full throttle on the ground, but in the air it was a lot less. Why did this prop have lower max RPM in the air than on the ground? Now, I have a possible explanation. I have a qualified guess. But do you? I would like to hear your opinion. Please leave a comment. So, what comes next? Well, I'm confident the concept is proven at sea level. It really works great, but it's obvious that it doesn't work at high altitudes. I think it's a right move to increase the preload to make the prop downshift a little later so you can actually use the benefit of 13 degrees. But we will need to use a softer spring, less stiff, and it's measured by a number called spring constant that basically says how many newtons of resistance you get per millimeter of compression. So a spring with lower spring constant would allow the prop to finish downshifting before reaching the full RPM. We'll build a new prop and we need to test it at high altitudes, which will not be me because I fly at sea level, but I'm sure we will find some pilots to be willing to do extensive, very boring measurements. Now, in order to make the measurements a little less boring and a little faster to perform, we also need to finish this little computer. This is a little thing that will monitor the RPM, it will monitor temperature and instant fuel consumption, and send all the data to the phone and to cloud so we can analyze on a computer. When this is finished, this will make all the measurements a lot faster, because you don't need to fly 30 minutes to burn 1.3 liters bottle of fuel. You'll have the reading instantly. So there are some exciting times coming ahead. This is still a little bit unknown. If you guys have any different explanation for the behavior of the propeller, what was happening, please let me know in the comments. I would really appreciate. Well, this happened to me so many times already. I truly believe that this project is at the end and we'll only fine-tune some little details. And boom, now it happened. There's a lot more research and development work needed. I already seen the light at the end of the tunnel, but there is not yet. I don't know when the project will be finished. I can only promise that this is our highest priority for now, and we will do our best. What you could do for us is hit the subscribe button, like it, share it, add some comment or even some advice if you can. Thanks for watching. Thank you for your support. See you soon.